The concrete walls are 15 feet thick, reinforced, poured in sections between 1913 and 1932. The Welland Canal, connecting Lake Ontario to Lake Erie through southern Ontario. The locks were designed to accommodate ships that didn't exist yet, vessels that would be built 20, 30, 40 years later. The engineers calculated maximum credible dimensions for future Great Lakes bulk carriers, then added margin. The walls have handled it. For over 90 years, Lock 7, the largest in the system, now provides the scale. The chamber measures 859 feet long, 80 feet wide. The lift is 46.5 feet, raising or lowering vessels from Lake Ontario elevation to the Niagara escarpment height. The concrete walls at chamber base are 15 feet thick. At the crest, 8 feet. The transition is gradual, stepped in sections every 10 feet of elevation. Modern analysis shows the walls were overbuilt by approximately 40%. For the hydraulic loads they carry, water pressure, vessel displacement, as gate operating forces, walls 9 to 10 feet thick at base would have been adequate. The engineers specified 15 feet. The decision wasn't arbitrary. The Welland Canal's location presented unique challenges. Southern Ontario's climate subjects concrete to severe freeze-thaw cycles. Winter temperatures routinely drop below -20 Celsius. Spring thaws bring rapid temperature swings. Water saturates concrete pores, freezes, expands. Standard concrete begins micro-cracking after 50 to 100 cycles. Yes, the canal walls have endured over 4,500 freeze-thaw cycles since completion. The thickness provides thermal mass. The outer few inches weather and spall. The interior remains at stable temperature, insulated by the sheer volume of concrete. This wasn't calculated precisely in 1913. Finite element thermal analysis didn't exist yet, but engineers understood the principle empirically. Thick walls survived longer in harsh climates. The data came from canal and dam structures across northeastern North America. Construction began in 1913. Now, the Welland Ship Canal Company had operated earlier versions of the canal since 1829. But by 1910, ship sizes had outgrown the existing infrastructure. The third canal, completed in 1887, handled vessels up to 255 feet long. By 1913, Great Lakes freighters were approaching 600 feet. The trend was clear. Ships were getting larger, and the canal needed to accommodate growth that hadn't happened yet. Chief Engineer William G. Chace designed the fourth Welland Canal with that future in mind. Now his specifications called for locks capable of handling vessels up to 730 feet long with 75-foot beam. In 1913, no ship on the Great Lakes met those dimensions. The largest freighters were around 550 feet. Chace was designing for ships that wouldn't be launched for another 2 decades. The concrete work consumed 19 years. Workers poured 3.5 million cubic yards of concrete across the 8 locks and associated structures. The mix design was conservative. Low water-cement ratio, minimal alkali content to reduce aggregate reaction risk, and extended curing periods. Quality control was rigorous. Batch records from 1920s construction show rejection rates around 12%. Any concrete failing slump or compression tests was discarded. The aggregate came from local quarries near St. Catharines. Crushed limestone and gravel, screened to specific size distributions. The cement was Portland cement from Pennsylvania and New York plants, shipped by rail. Each batch was tested before pouring. Compressive strength requirements were 3,000 pounds per square inch at 28 days, higher than typical for the era. When 2,000 pounds per square inch was standard for most structures. Workers operated in shifts. Summer pours ran day and night to maximize curing time before winter. The concrete had to reach sufficient strength before freeze. Winter halted most work. Crews covered partially completed sections with insulated tarps, sometimes heating the forms with coal braziers to prevent freeze damage during final curing. The labor force peaked at 2,300 workers in 1924. Wages averaged $4.50 per day for general laborers, $7 for skilled form carpenters and concrete finishers. Dangerous work. As 12 workers died during construction, falls from scaffolding, equipment accidents, one drowning when a cofferdam failed during Lock 4 excavation. The walls rose in 10-foot pours. Vertical construction joints were staggered to prevent continuous planes of weakness. Horizontal joints were keyed, interlocking surfaces that transfer shear stress between lifts. Steel reinforcement density varied by location. At the base, where hydraulic pressure peaks, rebar spacing was 6 inches on center in both directions. At upper sections, 12 inches. The steel wasn't there to carry primary loads. It was redundancy against cracking from thermal stress and shrinkage. The rebar itself was mild steel, not the high-strength alloys available today. Yield strength approximately 33,000 pounds per square inch. Diameter ranged from half-inch to 1-inch bars depending on location. Total steel consumption across all 8 locks, approximately 45,000 tons. The bars were tied with wire at intersections, creating a 3-dimensional cage that was positioned before concrete pour. The concrete cover, the distance from rebar to exposed surface, was specified at 3 inches minimum. This protected steel from moisture and chloride penetration. In practice, cover varied. Some sections show 2 inches, others 4. The inconsistency reflects hand placement and the difficulty of maintaining precise positioning during pours involving hundreds of cubic yards. The first ship transited the new canal in August 1932, the SS Lemoyne, a bulk carrier measuring 633 feet. Not the maximum the locks could handle, but larger than anything the previous canal accommodated. The walls handled the displacement loads without issue. Lock gates cycled, water filled and drained. The concrete performed as designed. Traffic built gradually. The Great Depression limited shipping volume through the mid-1930s. By 1940, annual tonnage reached 18 million tons, iron ore from Minnesota, grain from prairie provinces, coal from Pennsylvania. The St. Lawrence Seaway project, completed in 1959, connected the canal to ocean shipping. Traffic surged. By 1970, annual tonnage exceeded 60 million tons. The locks operate year-round except during winter maintenance. The navigation season typically runs from late March through December. Ice closes the canal for approximately 10 to 12 weeks annually. During peak season, a ship transits every 45 minutes. The walls endure continuous hydraulic cycling, chamber fills, ship enters, chamber drains or fills to match destination level, gates open, ship exits. Repeat. Approximately 40,000 cycles per year. But the test came later, as ships continued growing. By 1950, Great Lakes bulk carriers routinely exceeded 700 feet. The Edmund Fitzgerald, launched in 1958, measured 729 feet, within 1 foot of the canal's design maximum. Modern Seaway Max vessels, designed specifically for the Canal and St. Lawrence Seaway dimensions, reach 740 feet length and 78-foot beam. The walls designed in 1913 accommodate them with minimal clearance to spare. Vessel displacement has increased even more dramatically than length. The SS Lemoyne displaced approximately 15,000 tons fully loaded. Modern Seaway Max vessels displace up to 35,000 tons. The hydraulic forces against lock walls scale with displacement. When a 35,000-ton ship enters a lock chamber, it pushes water ahead of it. That water presses against the walls. The 15-foot thickness absorbs these dynamic loads, brief pressure spikes as ships maneuver, without the deflection that would occur in thinner structures. Lock operators report that modern vessels, and despite larger size, cause fewer wall impacts than mid-century ships. Electronic bow thrusters and computer-controlled positioning reduce collisions. But the walls still show impact scars, gouges in concrete where steel hulls scraped during entry. These superficial. The structural core remains unaffected. That margin wasn't luck. It was intentional overdesign for uncertain future demand. The walls have aged. Concrete spalling is visible on exposed surfaces. Freeze-thaw damage, chloride penetration from deicing salts, an alkali-silica reaction in sections where aggregate quality was marginal. These are standard deterioration modes for early 20th century concrete. Parks Canada and the St. Lawrence Seaway Management Corporation conduct structural surveys every 5 years. The reports document surface degradation, but confirm core integrity remains sound. Inspection protocols involve draining lock chambers for visual assessment. Divers examine submerged sections. Core samples are extracted and tested for compressive strength, chloride content, and reinforcement condition. The 2015 survey at Lock 7 extracted 18 core samples from various wall sections. Average compressive strength, 3,400 pounds per square inch, actually higher than the specified 3,000 pounds per square inch, suggesting the concrete has gained strength over time through continued hydration and carbonation. Chloride content varies. Surface samples show concentrations up to 2 pounds per cubic yard, above the threshold where steel corrosion initiates. But samples from 6 inches depth show less than 0.5 pounds per cubic yard. And the 15-foot thickness means chlorides penetrating from the surface have 15 feet to travel before reaching critical reinforcement near the interface. At current penetration rates, that would require approximately 400 years. Steel reinforcement corrosion is the primary concern. When concrete cover is compromised, cracked or spalled, chlorides reach the rebar. Corrosion initiates, the steel expands, further cracking occurs. It's a progressive failure mode. Maintenance crews patch spalled sections. They inject epoxy into cracks, apply corrosion inhibitors. The 15-foot wall thickness provides redundancy here. Even with localized reinforcement loss, the concrete mass carries hydraulic loads through compression. Inspections in 1975, 1995, and 2015 measured wall deflection under full load. Maximum recorded movement, 0.3 inches at Lock 7's base, within design tolerance. No structural reinforcement has been required. The walls built in the 1920s support loads they were designed for, without the retrofit work that plagues thinner, more optimized structures. The design philosophy reveals itself in the engineering calculations archived in St. Catharines. Chace's load assumptions included maximum ship displacement, full lock chambers, seismic events, ice pressure, and gate failure scenarios. The combined load case, all factors occurring simultaneously, was statistically improbable, but the walls were sized for it anyway. The calculations show safety factors between 2.5 and 3.0 for most load combinations. Modern practice uses factors around 1.5 to 1.7. The difference reflects changed risk tolerance and improved understanding of material behavior. Engineers in 1913 worked with larger uncertainties. Concrete properties varied batch to batch. Steel quality was inconsistent. Analytical methods were approximate. No computers, no finite element modeling. Margin compensated for uncertainty. Contemporary structures show the contrast. The Panama Canal, completed in 1914, used concrete walls 8 to 10 feet thick at comparable lock dimensions. Those walls have required more extensive retrofit work. Post-tensioning cables added in the 1960s, complete wall replacement at Gatun locks in the 2000s. The Welland Canal's thicker walls have needed only surface repairs. This wasn't incompetence. It was engineering conservatism from an era that had watched structures fail from underestimation. The Quebec Bridge collapse in 1907 killed 75 workers because load calculations missed critical factors. Engineers in 1913 remembered. They built margin into every specification. The Welland Canal walls stand as physical embodiment of that philosophy. Structures designed for maximum credible demand, not expected average use. The ships that didn't exist in 1913 now transit daily. The walls remain. Modern maintenance costs are substantial but predictable. The St. Lawrence Seaway Management Corporation spends approximately $8 million annually on Welland Canal infrastructure. Most funding addresses mechanical systems, lock gates, hydraulic rams, electrical controls. Yet the concrete walls require periodic patching and corrosion mitigation, but no major reconstruction. The 15-foot thickness, criticized as excessive when first proposed, now provides the reserve capacity that makes the canal viable for 21st century shipping. The maintenance breakdown: 60% mechanical systems, 25% dredging and channel maintenance, 15% civil structures including concrete walls. Wall repair costs average $1.2 million annually across all 8 locks. Compare this to the Panama Canal's expansion project, 2007 to 2016, which spent $5.25 billion partly to replace deteriorated lock walls from the 1914 construction. Future projections suggest the Welland Canal walls could operate another 100 years with current maintenance protocols. The limiting factor won't be concrete strength. It will be changing shipping patterns, environmental regulations, or economic shifts that alter Great Lakes trade routes. The walls were built to outlast the ships they serve. They're succeeding. If the Welland Canal were designed today, specifications would differ. Modern engineering optimizes for known loads with defined safety factors. Finite element analysis would calculate exact stress distribution. Wall thickness would be minimized to reduce material cost. The result might be adequate for current vessels, but less adaptable to future growth. Computer models can predict stresses precisely, but they can't predict how shipping will evolve over 90 years. The 15-foot walls weren't built for known loads. They were built for vessels that didn't exist, carrying cargo volumes that were speculative. That foresight, perhaps better described as caution, ensured the infrastructure remained relevant as shipping evolved beyond 1913 projections. Chace designed for maximum credible growth, then added margin. The ships grew. The margin proved necessary. The concrete endures. After 90 years of hydraulic cycles, freeze-thaw stress, vessel impacts, the walls function without structural reinforcement. They were built for ships that didn't exist. Those ships arrived. The walls were ready. They remain ready for whatever comes next.